Okay, that looks good. Let's try it. You're alive. Okay. Hello, Internet. Okay, so we'll check at the end of class and we'll see if it actually worked.
You said that video isn't available.
What?
Can you go back?
Play.
Yeah, because it...
Oh, because we're currently making the video?
Is it supposed to show there when we're making it, or not?
Well, it says live for 26 seconds. So yeah, the video's unavailable because you're currently playing it.
Okay.
I think. Because it says live and it's got the timer on top.
Does somebody want to try it?
Are you
Sure.
Is it recording any video or is it just audio?
I don't know, but we'll go on if you don't mind trying to hook it up. It's linked from Blackboard on my site. Let's see if you can find it. Okay, so we talked about most of the reactions. We're going to talk about a couple different categories. The aqueous reactions can have a few different categories. The precipitation reactions we've talked about. That's what we're going to probably focus the most on throughout the next week or so. But we should also look at some of these other types. Acid-base reactions, gas evolution reactions, and redox reactions. It works?
Yeah.
Great. Okay, so now I just got to remember how to do all those things every time.
Just go to the new dashboard.
Okay. Yeah, that's right. The like beta new dashboard thing. Okay. So there are various definitions of acids and bases. We're going to go through them more when we get into the acids and bases chapter. There's a lot of different ways, and in fact, the idea of acids and bases can be used to explain pretty much all of chemistry, depending on how you define that, because we're really just talking about electrons moving around. But specifically in this instance, we're going to talk about what we call the Arrhenius definitions, which is just that acids break up into hydrogen ions and bases break up into hydroxide ions. So we're just talking about hydrogen and hydroxide when we talk about acids and bases in this case. And there are going to be some consequences of that, and we'll have to revise the things we say today when we get into the next part. But there's another table from the book here where we can look at some acids and bases. And we want to define this idea of strong and weak acids and bases. Sorry, I will re-expand that so it looks regular again. Okay. So here are, like I said, some common acids and bases. Obviously, there's lots of acids and bases. But they're separated here into what we call strong acids and weak acids, strong bases and weak bases. The strong ones are written in black and the weak ones lower in red. What do we mean by strong and weak acids? Have you heard that term before? What does that mean? It's something that is commonly mistaken because it doesn't have anything to do with like the physical effects or the danger of these substances. It has to do with the electrolytic nature of the substances.
Is it the quantity or the amount of hydrogen or hydroxide ions that are put out by them?
That are put out by, that are formed in solution is essentially what it is. So strong or weak refers to the electrolytic behavior, not some other thing. Like everybody wants strong acids to be more corrosive, like they burn your skin or they burn through the floor or whatever. That's not true. That's not how that works. Strong acids mean that they break up completely into ions. So if we have HCl in solution, it's 100% broken up into H and Cl minus. Now, there's not actually H plus ions floating around in solution. It's H3O plus hydronium. But for our purposes, we can think about this like this at this point. A weak acid is a weak electrolyte, which means it only breaks into a little bit of ions. So compared to the HCl, if we take something like acetic acid, oops, if we have an aqueous solution of acetic acid, is actually mostly still together. And just a little bit separated. And I don't know if those numbers are exactly right. It depends on the solution and stuff. But basically, it's probably a much bigger spread than that. But an aqueous solution of acetic acid is mostly like sucrose, like just whole acetic acid molecules surrounded by water, and a little bit that's broken up, and a little bit that's separated. So you would expect a solution of weak acid to conduct electricity only a little bit, so very weakly, whereas a strong acid solution would conduct electricity very well. These are actually the only strong acids listed here, those 6 acids. All other acids are considered weak acids, which means they don't dissociate completely in water. At some point you will need to know them. You don't need to know them right now. I think when we get into the acid-base chapter, it'll become more important. So let's look. Yeah. So let's look at these acid-base reactions. Now we looked at one simple one already. Something like this. So there's a simple acid-base reaction. Identifying an acid-base reaction, well, it depends how much information you have. If you don't have the products, then you need to be able to identify acids. Luckily, you can already do that because you had to name acids in the previous chapter. So when you identify that there's an acid involved in the reaction and identify that there's a base, something with hydroxide or ammonia that's involved in the reaction, then you can identify that as an acid-base reaction that forms water. Sometimes acids have more than one hydrogen on them, but when they react with a strong base, they're always going to have all their hydrogens taken off. So for instance, if we have sulfuric acid, which is H2SO4, it is true that you could control the stoichiometry here and only put a little bit of sodium hydroxide in there and potentially be able to trap this at NaHSO4, sodium bisulfate, or sodium hydrogen sulfate. But for the purposes of an acid-base reaction, if that isn't specified in some way, you should always assume that you're taking off all of the hydrogens. All right, so notice here that the salt that goes along with the water is sodium sulfate, not sodium hydrogen sulfate. So we didn't just take one hydrogen off of the acid, we took both the hydrogens off the acid. We will get more into acid-base reactions when we do our antacid lab in a couple weeks. For now, the important thing is to be able to identify them and predict the products. The products are always going to be water and then the salt of whatever the leftover cation and anion are. All right, so next we've got gas evolution reactions. There are some compounds that generally give off a gas when reacted in a particular way. So for instance, carbonate ion when reacted with acid, like say HCl, it kind of looks like maybe an acid-base reaction or just a regular like replace the cations and anions type reaction. But what happens if you do that is you get hydrogen mixing with carbonate to make a compound and sodium chloride. So that's if we just switch partners there. The hydrogen goes with the carbonate, the sodium goes with the chloride. But this thing here, which is called carbonic acid, is unstable and it doesn't stick around like that. So that's really not the product of this reaction. This reaction spontaneously goes one step further to make carbon dioxide gas and water, and then it will still have the aqueous NaCl. So if we're going to balance this, there would actually be 2 here and 2 there like that. So the key in this one then is this carbon dioxide gas forming. So the net ionic equation here is carbonate ion reacting with hydrogen ions to form CO2 gas and water. So there are a couple categories of ions that you should always kind of take a quick look at or a little extra look at to make sure that you're writing the right products, because these are ions that can be involved in gas evolution reactions or in regular precipitation reactions. So there's a nice little chart in the book here of some of the compounds that undergo the gas evolution reactions. The key is looking for sulfites, carbonates, sulfites, and ammonia. When you see those and the intermediate product is as listed there, so you do whatever you're going to do like a normal aqueous reaction. If you find yourself forming hydrogen carbonate or carbonic acid, sulfurous acid, or ammonium hydroxide, know that that is not the endpoint of the reaction, that actually it will go one step further to forming the gas. So let's take a look at how that works. So let's say you've got, we'll look at this bottom example here. So let's say they have ammonium chloride and potassium hydroxide. Okay? And you're being asked to predict the products. What are the products of this reaction? So you first look at it and go, oh, okay, it's a regular ionic reaction. I've got ammonium chloride, potassium hydroxide, so I'm just going to switch the partners, and I get ammonium hydroxide and potassium chloride. Yeah? Great. So we go ammonium hydroxide and potassium chloride. But then there's this extra step that you need to take now when you're looking at these products and go, oh wait, is one of these products something special? Is it something that does something else? Is it something that's unstable on its own? And the answer is yes. Ammonium hydroxide is unstable on its own. And so the actual products of this reaction should go one step further, because the ammonium hydroxide is going to form ammonia gas and water, and then also the KCl. And as you work through the homework, hopefully you'll see some of these. And this is another nice thing about the online homework is, you're just kind of going through it, filling in your products from your reactions, and you write in ammonium hydroxide plus KCl, and it'll say wrong, and you'll go, well, what's going on? Why is this wrong? This is one of the things that often comes up is those intermediate products, those three intermediate products, are not stable on their own, and so they always take an extra step and go into a gas.
Are we going to have to write all of their states, like gas, liquid, aqueous, after every single one, or writing it down?
I believe the way it works in the homework is that it will not take away points, but it will remind you to add the states if it wants you to add the states. If I remember correctly, that's how it does it. It doesn't just say wrong, but it says like you forgot the states or something. But let me know what your experience is with it.
So is this just something we have to memorize and recognize?
Yeah, it's essentially those four things. So sulfites, carbonates, sulfites, and ammonium hydroxide. Whenever you make, yeah, Julie.
Will this slide be on Blackboard?
Yes, all the notes are always. I think, actually, you got a computer up. Can you check? Is it updating right now?
The notes.
Yeah. It should update as we do it, basically, on Blackboard.
So
This will be notes 4, I think.
yeah, it's updated.
Yeah, it's good. Okay. So yeah, it's there. Okay. Let's put all these together, and then we'll do the last part, which is the oxidation and reduction reactions, because that's a little bit different. All right, I'm going to write down some reactions, and I want you in groups or partners or however you want to work to try to decide what you think the products are going to be, including their states, meaning do you think this is going to be a precipitation reaction, gas evolution, whatever, acid-base. I'm not going to tell you which category each thing goes in. That's going to be up to you to try to figure out. Okay, so here we go. It's 4 enough? Okay, we'll stop there. All right, let's try those 4.
You're all welcome.
Can I make a lighter question? Can we get a visual representation of what happens when you take a solute, like, let's say potassium, and put it into water? Can we see the precipitate? Or can we see what happens?
Potassium doesn't form precipitate.
Or not
It's soluble.
I understand. Like, let's see it become soluble.
Potassium chloride in water?
Potassium.
Well, that's not dissolving. That's
I know what it does. but-
okay. That's a
But I
redox
just wanna do
reaction.
it.
I can show you a video of it.
Oh, it's not as fun.
We can't do that. It's too dangerous.
How about
But
sodium? How about just sodium?
But
How about just sodium?
we can burn magnesium. We can do that.
Because we didn't get our
Sodium.
we didn't get our demo the first day. I'm just saying you told us.
Oh, yeah, you're right. I do owe you that.
So I'm just saying, like,
We can do that one.
sodium. Sodium's not bad. So pure
Sodium's not
sodium-
too bad. I don't think we have any. Because, so the problem with those metals, I mean, besides the obvious danger of like explosion and stuff, the problem is that when they cause fires, those fires are actually accelerated by standard fire extinguishers. So you need special Class D fire extinguishers to safely do those. We don't have any Class D fire extinguishers here. I think we do have one upstairs by the metals, but we would have to be ready for that. But I don't know. If we have sodium, we can think about it. But I don't know if we have it or not. In grad school, I used to use a lot of rubidium and cesium, and that was always a little scary, like big quantities of it.
For what?
It's what we use for our reaction, like for starting materials. Yeah. Cesium is really cool because it's a liquid at room temperature, but it's gold. It like looks like gold, but we would have these big ampules of it and just be this liquid, and then you just knew that like if it hit the air, it would just explode, which is a little scary.
Yeah. It's easy. I mean, basically,
Do you know there's a fake video of that on YouTube that has like millions and millions of hits? There was a TV show in England where they were like, we're gonna drop all the alkali metals in water and like videotape it. And so they did the
cesium
right.
will react before it even hits the water.
Well, so they did like potassium and sodium, potassium, and then they said they like had these slow release capsules for rubidium and cesium where they would put them in the water so they would have time to get away before they dissolved, and they put them in like these bathtubs, and then they show it and it just like blows up. But somebody called them on it because they knew that's not what it would actually look like, and it turned out that they just faked it. They just used like dynamite or something.
So how often will there be something that's liquid other than water? Or will it always just be aqueous?
Depends on the temperature.
When we are identifying.
So for ionic substances, it's unlikely because most ionic substances are solids at regular things, right? And we're talking about when they dissolve in water. There's plenty of liquids. When we deal with more organic compounds, things like that, we'll use lots of liquids. But in these situations, we probably won't see a lot of liquids.
Okay.
Why did you have to get stitches in your
Oh, yeah. So a calorimeter. Have you ever, I don't know if you've ever used calorimeters, they're like steel things. I could show you this one up here when you pull it out of the lab. It's like a steel thing. You do a combustion reaction inside in a pure oxygen environment. You measure the change in temperature, change in capture. So one group got the lid on it a little stuck, and so I was trying to get it unstuck, and it was still a lot more pressurized than I thought, and so when I was kind of like messing with it, it like shot off.
At least it was your hand, not your eye.
Yeah,
or
yeah. And it wasn't like, it wasn't too bad, but like, they wanted to put a stitch in.
It's not hard, right?
No, it was, I think the students
You only, so which formulas do you want us to put? The complete?
Yeah, write the molecular equation balanced with the phases for those states. And I would also ask you, if you aren't using too many resources to do this, if you're just trying to do it, rate your confidence. Like, how confident are you that what you put down there is right? Just for your own, I mean, I'm not going to look at it, but just for your own use. Yeah.
Sorry, number 4, does the H, the Cl, and the O4, does that all break apart? Or does the H and the Cl go with the Cl?
What do you think?
I don't know, because
Okay.
well, I know one of the gas solution reactions is the H2CO3, and I'm guessing that's what it is. So then the Cl would be going with the Li.
Well, write something down so you can see what happens.
Oh, yes,
All right, what do you think about these? How is your confidence levels? Pretty good, all over the place? Some higher than others? Okay. Anybody want to say which one they're most confident about and propose an answer? Yeah.
number 4.
Okay, what do you think?
So first it was H2CO3 plus lithium. Is that hypochlorite?
Perchlorate.
Perchlorate.
Yep. So you initially wrote down like this and that?
Yeah, and then it was turned into CO2 gas plus H2O plus lithium perchlorate aqueous.
Right. So the ultimate product would be CO2 and H2O because that's what the carbonic acid would decompose into, and then the spectator ion here ions are lithium perchlorate, and then to balance that we would have 2 and 2. Number 1, feel good about that one? Okay. How did you, before you say what you got, how did you identify that one?
It's going to produce water. So
How did you know?
Because hydrogen and hydroxide will create water.
Okay, so you just traded them and then decided that would be water. Okay, so that makes it an acid-base reaction.
Calcium nitrate. So
Calcium nitrate. Yeah.
It's going to be the 2 in front of the. Yep.
All right, great. What else? Okay, go ahead. So.
Remember dose, add the potassium nitrate, add the 2 of those.
Strontium, yep.
Strontium sulfate.
Strontium sulfate, right.
And that is a solid.
That's a precipitate. Yep. How do we know that's a solid? Yeah. Is that what you're going to say? Go ahead.
Well, I have a question I can answer first.
Okay, go ahead.
It doesn't contain any of the exceptions, so that would be any of the alkali metals. So lithium, sodium, potassium, rubidium wasn't listed.
That's true, but that's not quite enough. I mean, you're right. You guys have the right answer in this case. We'll go back up and check that table in a second. What were you going to say?
I was gonna ask about the first one, so we can pick.
Okay, we'll go through this one first. Did you have a question, Ben?
Can you say why it's solid?
Yeah.
Just because, like, in the table, SO4 is normally soluble, but when it's paired with SR, strontium, then it becomes insoluble.
Yeah, so this is actually one of the exception ones. Sulfates are usually soluble, but there's a list of ions where when sulfate pairs with them, it is insoluble. And that includes the alkaline earth metals as well as lead and silver. So thinking about that one, because that could be tricky. So let's say, all right, you do this reaction, it's a quiz or something or an exam, and the same question, what are the products? So you can write the products, and then is this a precipitation reaction or not? So let's say you don't quite remember. The way that you can think, one way you can think through this is remembering, okay, well, nitrates are always soluble, so we know KNO3 is aqueous and is not a precipitate. So either strontium sulfate is a precipitate, or it is a no reaction where there are no precipitates here. And it might come to where you just don't remember from the table and you have to take a guess at that one. Right? Like that's sort of, if you don't know all of the exceptions, that's one thing that could come up where you go, I'm gonna have to take a guess. You still got a decent shot at it, right? You can guess if it's gonna be a precipitate or not.
Partial credit.
You get partial credit because you've written the whole equation, of course, right? But that is where one type, that's one example where you really would have to know that table well to say that strontium sulfate is a solid precipitate, because most sulfates are soluble. All right, so back to number 1. You had a question.
So I think I understand it, but I just wanted to double check.
Okay.
This one is an acid base because when you are doing the double replacement, H would go with OH, which is a base that can pair with an acid. So then can you assume that's an acid base, or
Yes.
if that was ammonia, or it's only
Right.
with hydroxide?
Ammonia also works, but with ammonia,
That's also a plus, right? So then that would.
it works a little bit differently. Yeah.
Okay.
Yeah. But the other thing you can see here is that we could definitely categorize those two reactants as acid and base, because We know HNO3 is an acid, starts with H, and we know that hydroxides are usually bases, so we could also use that to help make that distinction.
Okay.
Yeah.
So then the only time it would probably be different is if one of those ended up being the gas evolution.
Right, because sometimes acids are used in there too. And we'll see a couple other examples in the redox that we're going to look at in a minute too. All right, so on to the third one. Nobody felt good about this one? Are you fine? Okay, Nicolette? Okay.
So then I got an H3, which is a gas, plus H2O, which is liquid, plus HCl.
How did you characterize the state of AgCl?
I just knew from the table you showed us, because we also did that.
So you said that was solid, right? Solid precipitate. Okay. What do you think? So this one's close. Good job recognizing the silver chloride precipitate. That is true. But this one does not make a gas. It does not evolve ammonia. And the reason is because the other product that you make here is ammonium nitrate, which does not spontaneously break down into ammonia. Ammonium nitrate is used in fertilizer, for example. Ammonium hydroxide is the one that breaks down into ammonia gas.
Because that was, I think that was on the exam for
Yes.
fertilizer.
Yep.
That was in there.
Yep. That was a hard equation to balance. Yeah. Okay. So, think you got a okay start on doing these? You'll have a lot more practice tomorrow because tomorrow's lab is doing a whole bunch of reactions and writing them all out. So, we will. I know the way I said it made it sound like way less fun, but it is a pretty fun lab because you just get to mix a bunch of stuff, and then it'll give you good practice with this. It also I think really helps to see all those reactions to help remember like when you see what a silver chloride precipitate looks like. Hopefully that helps you remember that silver chloride makes a precipitate, and so you'll always think about that maybe.
So is it more important to actually balance our equations more than during the physical lab rather than today just trying to figure out what it turns into?
What it turns into?
Yeah.
Right, yeah. When you do the full post lab, you'll want like correct balanced equations. Yeah.
Sure.
All right. So let's talk a little bit about redox reactions, and then we'll get ready for lab tomorrow. Okay. Oxidation reduction reactions, sometimes called redox. We're doing them a little bit separately because they're not really their own category. Many of the reactions that we've seen already might also, well, not many of them, but some of the reactions we've seen already may fit also into the category of redox. Redox reactions are where there is a transfer of electrons. So electrons move from one species to another. And the tricky part about that is you have to be able to track where were the electrons and then where did they end up. So in order to do that, in order to track where the electrons go, we have to assign oxidation states. Oxidation states are a way of accounting for the electrons, and they're a little confusing to people because they sort of seem like charges because we write them as plus or minus a certain number, but they're a little different because they're not charges. You can have oxidation states in non-charged things, in molecular species. Oxidation states is more just like a method of accounting for where the electrons are and then where they go to. And it's going to seem right now like kind of an isolated topic just in these reactions. But if you go on in chemistry, if you take second semester, if you take organic chemistry, it's going to come up a lot. So it's worth learning, even though it can be a little bit confusing right now, and even though we're not going to use it a lot more this semester beyond this chapter. All right, let's talk about how we assign the oxidation states. So in a reaction, you want to look at each individual element in that reaction and decide what its oxidation state is at the beginning of the reaction and what its oxidation state is at the end of the reaction. And if it's changed, then you know that there has been a transfer of electrons. So let's go through how we assign oxidation states, and then we'll look at some examples, and hopefully you'll get a feel for how this works. Okay, so here are the rules to assigning oxidation states. The oxidation state of an atom in a free or pure element is 0. So if we have something like N2, we would say the oxidation state is 0. If we had something like aluminum, oxidation state is 0. If it's a pure element, the oxidation state is 0. Okay, second. The oxidation state of a monoatomic ion is its charge. Okay. That one's pretty simple as well. If you've got Na plus, oxidation state is +1. And if you've got S2 minus, oxidation state is -2. All right, so now we start getting to compounds. So if you've got a free element or a regular monoatomic single ion, it's pretty easy to assign the oxidation states. So now the next couple of rules deal with what happens when you have a compound. How do you determine the oxidation states of the different atoms within that compound? All right, so first, the sum of all oxidation states in a compound is 0 for a neutral compound or the charge of an ion. And we'll come back. I won't give you an example right now. We'll come back when we look at an example, and you'll see why that works. For in compounds, metals always have positive oxidation states. And just like their charges, group 1A metals are always have an oxidation state of +1 unless they're 0, unless they're like a pure element. But in a compound, they're always +1. And group 2A is always +2. Again, that's assuming they're in a compound. By themselves, they would just be 0. A couple more pages here. Okay, and then finally, the last rule is that we're going to assign other elements in order, and in this specific order. So first, fluorine gets -1. Then if there's hydrogen, it gets +1. Oxygen, -2. Group 7A, so the halogens, -1. Group 6A, the next group over, -2. And then finally, group 5A, -3. I know this doesn't make a lot of sense the way we've written it right now. Let's look at some examples, and I think you'll see how it works. Okay, let's assign oxidation states to the elements in 2 different carbon and oxygen containing compounds. So let's look at CO2, carbon dioxide, and let's look at CO, carbon monoxide. All right, so we take a quick glance through the rules. We're not dealing with pure free elements here. We're not dealing with monoatomic ions. Let's look at number 3. The sum of all oxidation states is 0 for a neutral compound or the charge of an ion. In fact, let's look at a third one here too, another carbon-oxygen compound. CO3 2-. So that means that those first 2 compounds, carbon dioxide and carbon monoxide, the sum of all the oxidation states has to equal 0 for those 2. And then for the last one, the sum of all the oxidation states has to equal -2, the overall charge of the ion. Okay. So then it says, in compounds, metals always have positive oxidation states. Well, there's no metals in these compounds, so we don't have to worry about that. So let's go on to this 5th rule. Assign these elements in order. So if we're looking at CO2, what this order tells us is there's no F, there's no H, but there is O, so we're going to assign O as -2. And then we're going to use that third rule, that the overall thing has to be neutral, to find the oxidation state of carbon. So what's the oxidation state of carbon in this compound? Whoa, a lot of different numbers. In this case, it is +4, because each oxygen has a -2. So if we take that +4, and then we add the 2 -2's, we get an overall charge of 0. Okay, so then how is carbon monoxide different when it comes to oxidation states from carbon dioxide?
Because carbon is +2, not +4.
Yeah, because it's CO instead of CO2, based on the table, we still assign oxygen first, but now carbon is going to be +2. You'll notice that carbon isn't even on that list, and that's because carbon can have a lot of different oxidation states. So carbon's oxidation state is going to be dependent on what else is in the compound with it. And then what about the carbonate ion? Once again, we assign oxygen as -2. Yeah, and carbon's going to be +4 again, because 4 plus -2 plus -2 plus -2 is -2, which we want overall. So we would say that if there were a reaction where carbon monoxide was turned into carbon dioxide, such as in the catalytic converter in your car, that is an oxidative process. That is oxidation, because carbon has increased its oxidation state. But if there were a reaction where, like a gas evolution reaction, in a gas evolution reaction, carbonate ion becomes carbon dioxide gas. That is not oxidation and reduction because nothing has changed its oxidation state. The oxidation state has stayed the same.
So if you got in CO2, if you got 4 plus negative 2 plus negative 2 equals 0, where does that 0 go and why is it different than that being negative 2 and then your O is negative 0?
Because the third rule here says the sum of all the states in the compound is either going to be 0 if the compound is neutral, or it's going to be the charge if it's an ion. And in this case, the first one, CO2, is a neutral compound, so the states have to add up to 0. But carbonate is a charged ion, so the charges have to add up to negative 2, which is the charge of the ion. Is that? All right, so let's show magnesium reacting with water. To form magnesium hydroxide and hydrogen gas. Okay. And we want to know if this is an oxidation reduction reaction, and if so, what's oxidized and what's reduced. We'll talk about how to define that in a minute. So to determine if this is an oxidation reduction reaction or not, a redox reaction, we have to find the oxidation states of each of the elements and then determine if they have changed over the course of the reaction. So let's assign the oxidation states for each element in this reaction. We'll make ourselves a little table. So that we have all the elements accounted for, and we're going to find the oxidation state of each one. So let's start at the left. Magnesium. What's the oxidation state of the magnesium in magnesium? Let's be careful here. Let's go back up to our rules.
Oh, no, it should be 0.
It's 0, because the oxidation state of any pure element, any atom in a free or pure element, is always 0. So that's 0. Okay, let's look at water. Water is not a free element. It doesn't have any metals or anything in it. So according to our table, what do we assign first, hydrogen or oxygen? Oxygen. So we assign the oxygen as -2. And then what does the hydrogen have to be to make for a balanced neutral compound? +1, right?
Wait, no, hydrogen.
I thought H
Hydrogen
was
is 2.
first.
Yeah, H is first. And then
Oh, H is first? Sorry. Did I mix that up? Yes, sorry. Okay. So we should have assigned hydrogen first and then recognized that oxygen would have to be -2 to make that work. The reason for that actually is really just one compound, hydrogen peroxide. If we try to assign hydrogen peroxide, you assign the hydrogens first, and that's how you get that oxygen as -1 instead of -2. Anyway, moving on. Magnesium hydroxide, what should the oxidation state of magnesium be here? Yeah, in this case it's +2 because we now have an ionic compound. The charge on magnesium in the compound is +2, and so its oxidation state also becomes +2. And what about the O and the H in hydroxide? So which one do we assign first? H first. We just make that +1 because that's what it tells us on the table. And then if we're looking at a hydroxide ion, what does O have to be so that the overall charge is the charge of hydroxide?
That's 4.
Negative
Or no, it's 2.
Well, so it helps with these maybe to break that down. Let's look at just the hydroxide ion by itself. Hydroxide ion is OH minus. So if H is +1, what does O have to be to have an overall -1 charge in that compound? -2, right. If O is -2 and H is +1, -2 and +1 makes -1 altogether, and so OH is -1 altogether, which is the charge on hydroxide. You see why that works like that? No. The oxidation states have to add up to the overall charge on an ion. So the overall charge on hydroxide is -1. So that means the oxidation state on oxygen and hydrogen have to add together to make -1. We assigned hydrogen as +1, so oxygen has to be -2, so that -2 and +1 make -1. And then finally, the hydrogen in H2, what's its oxidation state? 0, because it's a free element. Okay, so now we have all the oxidation states accounted for. Do we see any changes from the left side to the right side? Yes. What has changed?
Magnesium, the hydrogen.
Yeah, magnesium has gone from 0 to +2. And what else has changed? The hydrogen has gone from +1 to 0. Oxygen has stayed the same, and some of the hydrogen has stayed the same. All right, so that's evidence that this is a redox reaction. One nice shortcut to finding a redox reaction is any reaction that involves a free element has to be a redox reaction. Because if that free element changes in the course of the reaction, it either goes from 0 to something non-zero, or it goes from something not 0 to 0. So any reaction that you see a free element in, you should be expecting to find redox stuff going on there. All right, so for the last part then, we need to assign what exactly is the oxidation part and what is the reduction part. So let's define those and then look at this. Oxidation is the loss of electrons. Reduction is the gain of electrons. So in oxidation, a species will go from being less positive to more positive, and reduction will be more positive to less positive, or negative, same direction, different words. So like if something goes from 0 to +1, that's oxidation because it's lost electrons, become more positive. If it goes from -2 to -4, that's reduction because it's becoming more negative, it's gaining electrons. So in this reaction, what is oxidized? The magnesium is oxidized because it's going from 0 to +2. And then the hydrogen is reduced, going from +1 to 0. Oxidation and reduction always have to go together because the electrons have to go somewhere. So if something is losing electrons, then something else must be gaining electrons. So if you're looking at a reaction, you're trying to figure this out, if you find one of those processes, there's got to be another one in there too, if you're looking at an entire reaction. So if you see something being oxidized and you know something else is being reduced, if you can't find it, it's because something's going wrong with your oxidation numbers or something, but it's got to be there because they have to always go together. So just to make things a little bit more confusing, because that's what everybody likes, right? We also use a different form of words to describe these: oxidizing agent and reducing agent. The oxidizing agent is the one that is reduced in the reaction. And the reducing agent is oxidized. That's why it gets a little confusing, right? Because you're basically saying the opposite thing. The reason for that is that often we think about our chemicals and how they act on other things. So is there a thing in here? There isn't. But one of our GHS symbols is an O with a fire on it. And that's for things that are oxidizers. Have you heard of something being an oxidizer? If something is an oxidizer, that's an oxidizing agent. That is the thing that is reduced in the reaction. But the reason it's called an oxidizer is because it's basically taking electrons from other things. And that makes it very reactive often. So the oxidizing agent or the oxidizer is the thing that takes electrons and becomes more negative. The reducing agent or the reducer is the thing that gives up the electrons and becomes more positive. So that can be a little bit tricky to keep those terms together or straight. Okay, let's do another one for practice here. And then we'll talk about what's going on here. There we go. And then we'll talk about getting ready for lab tomorrow. All right, so this next kind of reaction actually fits in a different category called a combustion reaction. But what we want to know is it a redox reaction or not? And I'm sure you've seen reactions of this type before. I know we've done some when we balanced the balanced equations. But a combustion reaction is usually something made up of carbon, hydrogen, sometimes oxygen, and it reacts to form carbon dioxide and water. Reacts with oxygen to form carbon dioxide and water. You've seen reactions like that before, right? We've done some balancing of them, that kind of stuff. This is called a combustion reaction. The question is it also a redox reaction or not? So see if you can go through and assign oxidation states to all the elements in that reaction, and then decide what is getting oxidized and what is getting reduced. All right, let's go through this just because we're running out of time here. So let's do the easy ones first. When we see a compound or an element all by itself, we know that has to be 0. So the oxidation state of O here is 0 because it's just oxygen. Other ones we're going to have to use the rules to go through. So if we go back now to CH4, we always assign H first. So H is +1. If H is +1, what does that make C? -4, right. And then over here, between C and O, we assign O first as -2, and that makes C +4. And then in water, we assign hydrogen first to +1, and that makes oxygen -2. Is that what you got? All right, so is this an oxidation reduction reaction? It is. What is being oxidized? Carbon, right? Carbon goes from -4 to +4. That's a loss of electrons because it's getting more positive. Oxygen is going from 0 to -2. So that's an example of reduction. In fact, that word oxidation comes from the fact that oxygen is usually the one that's reduced. It's usually the oxidizing agent. When you react oxygen with things, oxygen is 0, and it almost always goes from 0 to -2, and so that causes something else to be oxidized, and that's where that word oxidation comes from, because this was discovered before we knew any of this stuff. We just knew that reacting stuff with oxygen did this to it, made these reactions, whether it's rusting or other types of oxidation. All right. Questions about that? Okay. So in categorizing things, just to help you out a little bit, most of the aqueous reactions that we talked about earlier today are not redox reactions. So when the ions are switching places and that kind of stuff, the gas evolution reactions, acid-base reactions, those are generally not redox reactions. They don't usually fit in those categories. Combustion reactions and some of these other kinds of things that we'll see do. So if you see a reaction that doesn't fit into one of those other categories, then there's a much better chance that it's going to be a redox reaction. If there is a reaction that very neatly fits into like the precipitation category and you can find the precipitate stuff, then chances are it's not a redox reaction. But you'll get some practice in looking at all that stuff in the homework and in lab tomorrow. So with our last few minutes, let's just take a look at the lab and what to do to get ready. Because we just had the exam, I didn't want you to have to do too much for lab. So we're going to be doing these reactions tomorrow. As you're setting up your lab notebook, if you feel comfortable writing all these reactions, then you're welcome to do so. Leave some room so that you can write your observations of what actually happens, what it looks like. If you'd rather not write the complete reactions yet, just because you don't feel comfortable doing that, that's fine too. Just give yourself space to do that when you actually do the lab. And it's in the post-lab that you'll end up doing all of the molecular and net ionic and complete ionic reactions. So you don't need to do that all for tomorrow. If the thing that I didn't pull it up yet. So the pre-lab for tomorrow. I'm going to say this is You don't have to have this done before lab tomorrow. There just isn't that much time to do it, and you could just kind of answer these questions as part of the lab tomorrow or for the post lab. The actual lab work part tomorrow, I don't think will take that much time, so you'll have some time to work on this and to work on the post lab and writing the reactions as well.
So we don't have to submit anything for the lab?
No, please submit your notebook, like getting your notebook ready for the experiment as usual, but you don't have to answer these questions for it.
Get to the chemical safety for every single chemical organism.
You know, I'm thinking no. I think no. We have in the past, like during the semester, we usually do, but I think given the time, I don't think that's reasonable. We'll just talk about the hazards before we start the lab tomorrow.
So pretty much we're just writing the procedure in there and obviously the title and the date.
Yeah, just prepare your notebook for lab. Yep. All right, sound good?
Yep.
Okay. I will see you tomorrow.